So
Uh,
our third and final presentation for today is going to be by Athiya, and she will present her work titled Text Normalization for Speech Systems for All Languages.
Thank you for that introduction. So just a refresher for everyone, I'm sure that this can be redundant, but text normalization is also often known as standardization. This is basically just mapping non-standard words to standard words. And why is this important? This is important because most text-to-speech systems are only limited to standardized words, which means they can't spell out numbers like 5 or 25, things like that, without additional information or encoding. So it has been found that major degradations of perceived quality in text-to-speech systems can be traced to problems involving text normalization. And there has been previous work that tries to solve this, but a lot of the methods have poor generalizability to new languages, or they require experienced software developers to implement. So for example, the neural approaches, they usually require loads of data as, they train a text normalization task as a supervised learning task. So of course that requires a lot of labeled data, and we might not have that privilege for low resource languages. One related work that I'd like to point out is the FSD-based verbalizers. So they frame the text normalization problem as a data collection problem, where they collect language-specific data from native speakers, and they use this information to parameterize a verbalizer template. But then this will be further processed by formal language experts to develop the final text normalization system. So the method they're proposing today takes in the idea of text normalization as a data collection problem as well, but we improve it further by providing a user-friendly interface, which allows anyone with minimum coding technical experience to easily amend the provided information and add information on text normalization, and they can correct it for any mistakes easily. So the main question that we're trying to ask is, given access to a native speaker, what are the most important questions we should ask them in order to perform basic counting in the language without having to write additional code? So why is this challenging? First, I'd like to point the idea of semiotic classes, which are groups of non-standard words that occur in text, and they are distinguishable by patterns within the non-standard words. So for example, like a time semiotic class usually have 2 digits followed by a colon, followed by another 2 digits, and sometimes there would be a PM in the end. Or the money semiotic class would contain a currency symbol or the abbreviation of the currency at the end. And this is not an exhaustive list. These are just some just to highlight what semiotic classes are. And first, why is text normalization challenging is because standardizing semiotic class is often ambiguous. So if you can look at the time, it says 12:15, and say that this is 12:15 in the morning. Someone might say this is 12:15 a.m., or someone would say it's a quarter past midnight, or someone would say it's 15 minutes past 12, and they're all correct. So the stylistic differences is what makes this task challenging and slightly ambiguous. And of course, when you go across semiotic classes, it becomes even more difficult. So for example, $5, you'll have the currency symbol before, but when you say £2, the pound abbreviation would come after, but they'll both be normalized after the number normalization. And of course, normalization rules for different semiotic classes are different, like how phone numbers are read out individually. But for example, time, the first 2 digits are read out as a cardinal number, followed by a pause, and then followed by the next 2 digits read out as a cardinal number. And when we go to different languages, it even becomes exponentially difficult. First, different languages have different counting systems. So they might count in different number bases. So in English, we normally say 80 and it's base 10, but French, people speak French, 20 is quatre vingt, which means 4 20s. And even languages that have the same base don't really agree on the trunking system. So for example, the number 125000, an English speaker would read this as 125,000, and it would be chunked by the thousands. However, a Mandarin Chinese speaker would read this out as 1 wuqian, which is 12, 10, 5,000 and 5,000. And similarly in Hindi, this would translate into 1 lakh and 25,000. So they don't even use, generic like thousands, hundreds. They have a different denomination, lakh, which denotes 100,000. So we propose a method to collect data regarding the counting system and additional information that helps us to denote this different semiotic classes from a native speaker without any coding experience to have a generalizable text normalization system. And from this method, we would like to answer the following questions. So which non-standard words appear in text? How do we ask questions to get our answers? How do we make it easy to answer such questions? And how do we address variability? And how do we extend this to full front end? So this is the high level methodology. So for the data collection process, a user through a web application, the user is able to pick a language from a drop-down menu. The user will download a CSV template and fills the relevant fields containing the digits and the different semiotic classes. And the user uploads the CSV template, and then it would be saved with a unique identifier. So the main goal of the data collection process is to obtain sufficient information from a native speaker in order to map non-standard numerical text to its standardized form, ideally by asking the minimum number of questions. So after looking at several high-level languages, we decided that it's enough to collect the digits 1 to 100, as they don't vary much as we go to larger numbers. And additionally, we asked them to input additional symbols such as currency, how to read the decimal point, how to read the percentage sign, and more. And this is just like for the interest of time. We know that demos take a lot of time, so I took the liberty to screen record a video. So that's how the user selects a language. They download the CSV file and they would fill it in one by one. They would upload it and they can see the uploaded table. So that's how the data collection process is. It's pretty straightforward. And then the CSV file will be saved in our system. And then just briefly to the text normalization algorithm, we're not going to go through this too thoroughly, but basically when the user uploads the CSV file, the backend will pass information into a hash map to be normalized using a Python script. And at the moment, I think the semiotic classes that we can handle are whole numbers, phone numbers, currency, floating point numbers, time, and percentages. And I think it involves date as well. And first, when the number gets a cardinal number, the algorithm takes into account how the numbers are chunked. And this is one information that we ask of the user in the field and processes each chunk accordingly. So for example, the number 1, 2, 3, 4, 5, 6, you'd process 1, 2, 3, which is 123, and it would take into account the position. So it'd be 123,456. And then it will concatenate that. And of course, for the different semiotic classes that are denoted by special symbols, it will take into account the surrounding symbols. So for example, of decimal points, currency symbols, percentages, and whatnot, and they will process that accordingly. So for currencies, floating point numbers, and percentages, the non-standard text will be split depending on the position with respect to the decimal point. But there's a problem with, again, style problems. So for example, the currency $2.52, just for simplicity, what our algorithm does is it would say $2.52, but I feel like a lot of people would be preferring $2.52. However, this would make the problem exponentially difficult because we would need to collect information on more fine-grained currency denominations like cents and pence and whatnot in different languages. And phone numbers will be normalized to individual numbers. So in this slide, we can sort of see that these two semiotic classes are way more ambiguous. So for example, for phone numbers, different countries write their phone numbers differently. So for the US, they would normally denote the area code inside of parentheses. However, we also have like lengths of hotlines which are short, like 911. And some countries or some phone numbers are denoted as international numbers with the plus country code and then the phone number. So that's what makes this difficult. And text belonging to the time semiotic class, they're also quite ambiguous, as mentioned in the previous example. So for example, 2053, some people would understand the time is now 2053. However, people who are more accustomed to the 12-hour time zone, this wouldn't make sense to them, and they would prefer it's 8:53 p.m. or it's 8:53 at night. So after we collect this data and pass it using the text normalization algorithm, the user will use the front end to input a non-standard word, and then the algorithm will pass it, and then a flight synthesizer will read out to the user the normalized form, and then the user provides a correction. If necessary, place the corrected version so they can make sure that the correction is correct, then submits the correction. So we provide a feedback collection system in the website, and they can amend it, and then they will able to submit basically if they found something wrong. So I think there's another video of how this would look like in the web app. So once you can see that they uploaded the CSV file, they will be able to type in any number, and then they can play it out loud. And if that sounds wrong to them, they can give a correction. That keep and then they can submit the correction, and this would just update a CSV file in our system, which includes all the corrections made by different users across different languages. So as you can see, there has been several corrections for the Indonesian language, and we can see from here, from the table, we can perform qualitative evaluation on the different corrections. And one thing that I can see as an Indonesian language speaker is that the errors have something common, is that every time someone does 1,000, the algorithm passes it as 1 and 1,000. However, the verbalization is actually not the Indonesian version of 1 and 1,000, which is 1,000, but they concatenate it somehow, which is called like 1,000. So that's why these methods are good, because you can see what the errors have in common, and then we can somehow, given enough users, enough feedback from erroneous normalizations, this data will allow us to identify common mistakes that arise from text normalization or specific languages. And eventually, if we find enough problems, maybe it's an algorithmic problem, like the text normalization algorithm has a bug that we haven't seen before, or we can add new fields to collect more information on the CSV file. So this can be sort of like different ways of saying a particular. So for example, like how in English, we don't say 1 but we say 11. But then the rule becomes more standardized as we go to 21, 31, 41, and so forth. So maybe we can take into account those kinds of differences. And I think, as mentioned previously, we believe that these differences only lie between the 1 and 100, but turns out for the Indonesian language, like the word for 1,000, 2,000, like the word for 1,000 is different than how we thought it would be. So these are just like basically the results from the discussion from the research questions that we managed to answer by using the system. So first, which non-standard words appear in text? We can see that the different non-standard words can be classified into the different semiotic classes, and the presence of a semiotic class highly depends on the corpus the text originates from. So for example, if you were reading a science textbook, you would probably have more measure type of semiotic class, so you would have 2 kilograms and whatnot. But for news articles, for example, you would have more date and time. And of course, there are other ambiguities as well. So for example, the time 1910 could be a time, or it could be also a verse from the Bible. So again, I feel like the source of the where the text where the non-standard word come from needs to be taken into account as well. So how do we ask questions to get our answers? So we collect the information from a native speaker through a CSV file that's available in the web app, and then they can input information such as the digit normalization from 1 to 100, common symbols, and how to read them out. And of course, it will allow the user to provide feedback in case they hear the normalizations is wrong. And I think one important question here is, why did we choose to, read out the word? Because I feel like I thought that, like the normalized version in text would be sufficient. But as a native language speaker, normally you don't really think about how you would normalize a number like consciously. So when you hear it out, it would be easier for you to point out, oh, this sounds wrong. And that's easier for you to spot it instead of you reading it and like, yeah, that's right with respect to linguistic rules. So when you read it out, it does help really identify, which part of the normalization is wrong. So how do you address variability? So we understand that different people speak different dialects, come from different places of certain country that speaks a particular language. So we decided for each user, we store multiple tables for various languages, and we'll take the most common mapping for each of them. And this will also solve the issue of dialectical variation that may arise from the variety of input collected from the native speakers. One important thing about saving multiple tables is we can also address the issue of this is going to be publicly available, like the web app is going to be publicly available. So how do we keep malicious actors from messing up with the tables? So unless they submit hundreds and thousands of tables, hopefully that will have more good ones, and we can take the most common mapping, and that would be used for the normalization. So how do we extend this to full front end? So there are a lot of non-standard tags that are not covered by the different semiotic classes, and even we weren't able to cover all the semiotic classes just for the interest of generalizability and as a proof of concept that this idea works. So there are other non-standard text forms, such as shortened forms or abbreviations that are commonly used, like how people would say like dept, and it would mean department, or there would be some like organizational names that are usually abbreviated like CIA and things like that. And we would like to extend our method to be able to capture these nuances as well from multiple languages using the same data collection process. So hopefully, I think that's all. I think we should have time for questions.
Yes, thank you. That was a wonderful presentation. We have a few minutes for questions.
Questions?
So I have a question. It's about what scale the system can support right now, and if there are already any mechanisms in place to support a larger set of languages or data sets in the future.
So right now, I think because we're using the flight synthesizer, and this would be hosted on Alan's server, which contains the synthesized voices already. So I think it could support 700, and CSV files are relatively small. And again, this is not like thousands of rows of data. I think at the moment we have around 150 rows, which includes the verbalized version of the numbers 1 to 100, and then there like the verbalizations of symbols like percentages and dollar signs and things like that. So it's relatively small, and again, we would store multiple tables of the same language if we have different native speakers coming in and filling in the table, and eventually we'll just have a script that gets the majority translation of a particular digit. So assuming eventually one language would have one table, that would be fine. And of course, because we're trying to aim for, so basically this is not a perfect solution. So there will be mistakes, which is why the feedback mechanism exists. But I think this is more like it's better for the synthesizer to say something that's almost correct instead of not saying it at all for a low resource language. So for example, for the time, right? So 2053 in English, for someone who prefers the 12-hour system, it would say, 8:53 p.m. But as an Indonesian, we don't use AM, PM. We use the morning, afternoon, evening, and night paradigm. So instead of 8:53 p.m., it would say 8:53 in the evening, which is more natural for Indonesians. But right now it would just say 20:53, which is not ideal for, different languages, but it would still make sense. Yeah.
Okay, thank you. That makes sense. Do we have any other questions from the audience? All right, I guess we still have a minute, so I have another question. I can already think of a lot of potential applications just from the previous presentations we've had in the last session, the keynote, low resource languages and such. But I was wondering if you could make a comment on where you see this work fitting into the broad speech for social good narrative. What is your ideal impact or outcome for this work?
So I think what flight synthesizers are used for they're used for text-to-speech systems on most cheap Android devices. And these cheap Android devices are more popular in like very regional areas. People with lower income. So normally like these places might also speak a language or a dialect that's not high resource. And if we are able to do this, this means that we have a working text-to-speech systems for people who actually use these devices. So I think that's where this would come in.
That makes a lot of sense. Thank you. All right, I think that's all the questions we have for now. Thank you for your presentation.
Thank you.